Hello and welcome to the screencast for Chem Activity 27, Intermolecular Forces. Why do liquids stick together? This is the screencast for Allied Health Chemistry, Chemistry 120 at Missouri Southern State University, and I'm Dr. Michael Garut. Model 1 shows water at room temperature in Part A, and in Part B, water after some heating. Pause the video and answer question 1. Pause now. Okay, hopefully you can dissect what this diagram is trying to tell you. The water is mainly in a liquid state. You can tell that because most of the water molecules are here in the shaded portion, which is supposed to represent the water in the beaker. Of course, I can't show you the 10 to the 23rd, 10 to the 24th water molecule, so each of these is going to represent a large number of them. Number 2, what do the small arrows represent in Model 1? So you see all these small arrows, and so the question is, what do you suppose those represent? Pause the video and write your answer now. Okay, do you agree with me? I suggest that those arrows indicate the direction of motion. I wrote the motion and direction, right, of individual water molecules. So they're moving constantly in different directions. You might have thought that the arrow indicates polarity, but if you looked at the arrows, they're not all like this one is pointing away from a hydrogen, this one's pointing away from an oxygen, this one doesn't seem to have much of an arrow at all. So polarity would be the same for any water molecule, and since they're different, it couldn't be that. So it seems that motion is the best conclusion to make there. And if you look at Part B, you see the same thing, that the arrows show that water's moving in a particular direction. Okay, number 3. Note the water molecule in Model 1A indicated by the large arrow. That's right here. What's different about that molecule compared with the others in the container? Pause the video and write a sentence. Pause now. Okay, hopefully you noticed that that water molecule is outside or above the surface of the liquid. So you could have said it's above the surface of the liquid. I wrote this molecule is not within the liquid. And so what that must mean is it must be in the gas phase or the vapor phase. Number 4. How do you suppose that molecule obtained its location? So propose an explanation for that. Pause now and write your sentence. So is this what you said? I said, this molecule of water evaporated or vaporized from the liquid. Notice how those words evaporated and vaporized both have the same root in them, vapor. Evaporated, vaporized. They mean slightly different things, but they're similar. You might, if you were just going for a stretch, you might have said, oh, well, that water molecule came in from the air. And that is another explanation for how it got there that's reasonably valid. If you wrote that, I understand why you said that. Number 5, when water evaporates, oh, look at that. When water evaporates, are any OH bonds within a water molecule broken? So consider also this sentence and then answer question 5. Pause now. Okay, so if I look at this molecule of water, it's still water, right? It's still got 1 oxygen, 2 hydrogens, so no, it's still water. No OH bonds are broken. So evaporation doesn't mean that we're splitting water up into atoms or any components. It's just the whole molecule of water just coming away from the rest of the water molecules and jumping off into the gas phase. Number 6. How does the process of evaporation change when heat is applied? So that's supposed to be illustrated by this picture. So pause the video and write a sentence. Pause now. Okay, here are a couple of things you could have said. You could have said it happens much more quickly, or you could have said many more water molecules enter the gas phase. I think both of those are reasonable conclusions from this picture. You can see lots more water molecules in the vapor phase after heating. Number 7. On average, are the water molecules closer together in H2O-L or H2O-G? Recall what those letters mean. Okay, I won't even pause here. I think you got the idea. They're closer together in the liquid, right? In the gas, they're further apart. We saw that also in the previous activity, right? The gases were in the vapor phase, the molecules are far apart, and in the liquid phase, they're close together, right? All right. Number 8. On average, would you expect the attractive forces between the molecules, intermolecular forces, to be stronger in H2O liquid, liquid water, or H2O gas, gaseous water? Explain your choice. Pause now and write your answer. Okay, I'm sure you said something along the lines of this. I said the intermolecular forces would be greater in liquid water because the molecules are closer together. Imagine what would the forces be? They would be attractive forces. I said that here in the question. Much like two magnets can attract each other, and the closer you get the magnets, the stronger the attraction is. If you've ever played with magnets, you know that if you're pushing two of them together on a table, at some point they begin to attract and they pull together. But if they're far apart, that attraction is pretty small. The attraction only gets large when they get really close together. And it's the same for water molecules. All right, so we're ready to move on with Model 2. Boiling points and water solubility of some selected compounds. To a large extent, the boiling point of a liquid is determined by the strength of the intermolecular attractions in the liquid. These attractions are determined by the size and structure of the individual molecules. And then we have a whole table full of molecules in 4 categories. Category alkane, alcohol, amine, and ether. In this table, we have a condensed Lewis structure to show you what the formula is and how the atoms are bonded. We have the molecular weight, also known as the molar mass. We have the boiling point, and we have the water solubility. In this case, we have this infinity symbol, which is a little bit different than the proportionality symbol that we saw in the gas law activity, but very similar. When the liquids are infinitely soluble, that means they are miscible. Miscible is the word that means you can mix them in any proportions and they will completely mix. They will not form layers like oil and water. Okay? So we're ready to move on with the questions. Number 9. Recall that the electronegativity of carbon and hydrogen are roughly the same. We don't need to know the numbers necessarily, but they're pretty similar. And nitrogen and oxygen have significantly higher electronegativities. For each type of compound, alkane, alcohol, amine, ether, predict whether or not the compound is expected to be polar or nonpolar, and look at the structure in order to do that. So pause the video and write your answer for all 4 categories. Okay, what do you think? I have 3 polars and a nonpolar. If I'm looking at alkanes, all they have are carbons and hydrogens, and the electronegativity of carbon and hydrogen are very similar, so those bonds are not very polar. And even if they were, the shape is tetrahedral, and most of those polarities will cancel out. The molecules are quite symmetrical. When I look at the alcohols, they have oxygens bonded to carbons and hydrogens. Those bonds are polar. In the amines, I have nitrogens bonded to hydrogens and carbons. Those bonds are polar. In the case of ethers, I have oxygens bonded to carbons on either side. Those bonds are polar. Does that make sense? So anytime I have an alkane or just a hydrocarbon, which would be other kinds of molecules we haven't learned yet, but anything that just has carbon and hydrogen, probably going to be nonpolar. Okay, number 10. For a given type of compound, so within a category, A, how does the boiling point change as the molar mass of the compound increases? Pause the video and answer this question. Pause now. Okay, you say that the boiling point increases, correct? So if I look at the molar mass and the boiling point, they increase together. I could say they're directly proportional. Part B. Do the intermolecular forces, the attractions between molecules, increase or decrease as the molar mass increases? So circle a choice and then explain. Pause now. So did you say increase? As the attractions increase, more energy, such as heat, is required to boil or vaporize the liquid. So if I think about what boiling is, looking at the picture, it's giving those molecules enough energy to jump off the liquid and go off into the vapor. And so the more they stick together, the more energy you'll have to add to make that happen. And the sticking together, that is the intermolecular attractions. Hence my sentence, which says that as the attractions increase, more energy is required to boil or vaporize the liquid. This is a pretty key concept and something that you'll want to have firmly in your mind about intermolecular forces and energies as we go through the class. All right. So, working with your partner or alone, choose one alkane, one alcohol, one amine, and one ether that have about the same molar mass, and rank them in terms of relative boiling points. So write your 4 compounds and then rank them. Pause now. All right, so I picked pentane, 1-butanol, butylamine, and diethyl ether. That was the easiest one for me to find. Pentane, molar mass of 72, 1-butanol 74, butylamine 73, and diethyl ether 74. So very similar in their molar mass or size, but their boiling points are quite different, and I wrote them down here, and then I wrote them from highest to lowest. So 1-butanol, butylamine, pentane, and diethyl ether from highest to lowest. All right? Number 12, repeat that with another set of 4 compounds. So pause the video, find your set of 4 compounds, a different one than this one. Pause now. All right, this time I picked 1-hexanol, hexylamine, heptane, and dipropyl ether, all of which are either 100, 101, or 102 grams per mole. And this time I ranked them going across with a greater than symbol. So 1-hexanol is a greater boiling point than hexylamine, which is greater than heptane, which is greater than dipropyl ether. So do you agree with that? So let's go on with number 13. Does polarity in molecules tend to increase or decrease the strength of intermolecular attractions? And then write that down in a sentence. Pause now. Well, so I had to pick increase or decrease. So since I have to pick one, I picked increase. Why did I pick increase? When I look at the ones that I listed as polar, the only ones I listed as nonpolar were the alkanes, which is this one, nonpolar, and this one, nonpolar. So in general, 2 of the 3 polar ones are more have higher boiling points and therefore have more intermolecular attractions. So I think that it's fair to say polarity tends to increase the intermolecular attractions. It seems that these ethers don't fit that trend, and so this, science goes this way. You make generalizations, and then sometimes there are exceptions. One thing that comforts me is that the exception is pretty small. So like here, pentane versus diethyl ether is only different by 1 degree in the boiling point. Here they're only different by 9 degrees compared to a much larger degree changes in the others. But there certainly is an exception there, so I understand why that one is a little challenging to answer. But it's true that in general, polarity tends to increase the strength of the intermolecular attractions. Okay, so based on the relative boiling points, write the numbers from 1 to 4 under the functional group names below, with the number 1 being the group with the most intermolecular attractions and 4 being the least. Pause the video and write 4 numbers now. Okay, so are these the numbers you have? In the alcohols are clearly the highest boiling points. The means are clearly the second highest. Alkanes and ethers are pretty close, so I'm going to have to go with 3 for alkanes, slightly higher in both these cases. Not much difference in those, but quite a big difference between 1, 2, and the other 2. All right. So number 15. For each of the 4 functional groups, circle each type of bond contained in the molecule. And you can go back and look at Model 2, which shows you the shortcut or condensed Lewis structures. Pause now, and I'll give you a hint. There should be 8 circles. Okay? Pause now and circle 8 things. Okay, are these the 8 circles you have? Let's just double check yours and match them to mine. If I just look at the structures of ethers and alcohols. Whoops. So when I look at this shortcut structure, CH3CH2OH, this O is connected to the C in front of it and the H after it. So it does have CO and OH. When I look at the ethers, this O is connected to the C before it and the C after it, and O only has 2 bonds. So there's no H connected to O in ethers. If you're not seeing that, you can write out the whole structure like CH3, and then the O, and then the CH3, like so. Which shows you that the O is connected just to carbons and not to any hydrogens. Okay? So based on your answers to 14 and 15, which 2 types of bonds that you circled in 15 are present only in the molecules containing the 2 functional groups with the strongest intermolecular attractions? Pause the video and write your answer. Okay, you got this one. In the alcohols, they have OH bonds. Nothing else that's listed has that. In the amines, which is the second most, they have NH bonds. Nothing else has that. So there must be something special about those. And in Model 3, we're going to just read some paragraphs that explain what it is about those particular types of bonds, or how we recognize the particular types of bonds that have those strongest intermolecular attractions. So what you need to do is read through this model. So pause the video now and read this model, read the types of forces. These are things you're going to need to commit to memory and be able to apply. So pause, read that now, and think about it. So there are 3 types of intermolecular forces, and the strongest one is known as hydrogen bonding. And that's what you identified in this last activity, or this last model. When you have hydrogens bonded to oxygens or hydrogens bonded to nitrogens, that's when you have the capability for hydrogen bonding. It turns out to also work when it's hydrogen bonded to fluorine, but since fluorine only makes one bond, the only compound you can make with hydrogen bonded to fluorine is HF, and so that's not very important in the universe because it only makes one possible molecule, and that's a very toxic molecule. If you get that stuff on you in any large quantity, you're probably dead. So we don't usually have to worry about that. We just usually think about oxygen and nitrogen. In this paragraph, it describes what a hydrogen bonding interaction is. And it's an unfortunate name, hydrogen bonding, because it's not really a bond. It's really a strong attraction, a strong intermolecular force. We call it a hydrogen bond because it's almost like a bond. It's just a really strong, it's like it's like much stronger than other intermolecular attractions, but still much weaker than a covalent bond. And in order to have a hydrogen bond, you have to have the HN or the HO bond, but you also have to have a lone pair of electrons for it to be attracted to. I'm going to draw a picture for you. If I draw a molecule of water, and I know that the molecule of water is bent with 109-degree angles because there are 4 domains of electrons. And if I draw another molecule of water over here, I know that it is also bent and it has 4 domains of electrons. So the particularly strong attraction has to be from one molecule to the other. That's what makes it intermolecular. Inter means between. So it has to be the H bonded to the O, and then it has to be attracted to a lone pair on another molecule. And we usually indicate that with a little dashy line, like this. This is how I would indicate a hydrogen bond. It's covalently bonded to one oxygen. It has a hydrogen bond to a lone pair on a different molecule. Do you see how that works out? And notice how I've made this longer than this, because this would be further apart, because it's not a covalent bond, so it's not quite as strong as a covalent bond, so it's further away. Just like the attraction is going to be less when it's further away. Just like 2 magnets, the attraction is less when they're further away. Okay? Then we also have 2 other types of intermolecular forces that you're going to memorize the definitions of, called dipole-dipole forces and London dispersion forces. Sometimes people like to abbreviate these London dispersion forces and these intermolecular forces. So IMF or LDF, just because we get lazy and we like to have abbreviations for things. Okay? So, number 17. What is the difference between intramolecular bonds and intermolecular forces? Pause the video and write a sentence. Pause now. Okay, so we know the prefix intra and the prefix inter. Intra means within, like intramural sports means sports within the same university, whereas intercollegiate athletics means we're playing the other universities. Okay, so intramolecular means within a molecule, such as covalent bonds. Another example would be ionic bonds. While intermolecular means between molecules, such as the 3 types of intermolecular forces listed above. I abbreviated because I couldn't fit that in my space. Okay, rank these intermolecular forces in terms of their typical relative strengths. Pause and do that now. All right, this is my order. Hydrogen bonding is given as the strongest. I think we've seen that throughout this activity. Dipole-dipole is usually considered the next strongest, and London dispersion forces the weakest. On the other hand, when molecules get really large, these can also be very large. We tried to sort of normalize for that in this activity by looking at things that were roughly the same size. In general, this is the general order. If you switched these, I understand why you did that. This mostly depends on the size of the molecule, whereas this one depends on the polarity. And so this is usually considered a stronger relative strength if there's just one instance, versus this one that happens, multiple instances. When the molecules get large, it happens over and over again. In terms of intermolecular forces, write an explanation of the trend you described in question 13. So question 13, with some exceptions, polarity tends to increase intermolecular attractions. So write an explanation. Pause now. Okay, after we talked about question 18, I think you probably got something like this for question 19. Let's move on to number 20. Go back and revise your answers on this page if you need to. Pause if you need to. Then go on and answer question 20. Do parts A through D. Pause now. Okay, is this what you got? 1-pentanol for the heaviest alcohol with 5 carbons, and hexylamine for the heaviest amine and 6 carbons. Let's look back at that. So this question said, assume that anything that is more soluble than about 1 gram per milliliter, 1 gram per 100 milliliters is considered to be soluble. We have to cut off somewhere, right? So ethanol, infinitely soluble. 1-propanol, infinitely soluble. 1-butanol, we can dissolve about 6 grams of it in 100 milliliters of water. 1-pentanol, we can dissolve about 3 grams. 1-hexanol, about 0.6 grams. So what we're saying is we're cutting off there and saying these are soluble, and we're saying this is insoluble. You see, it's not black and white. Like most things, it's shades of gray. So, but 1 gram per 100 milliliters, that's like 1%. So, okay, if 99% of it is not dissolved, then we can call that insoluble. You see why we picked 1 gram per 100 milliliters? Okay. And here, the cutoff is here. So, this is insoluble, and this is soluble. All right, so that's how I answered that question. So, considering those answers, the presence of one polar functional group is sufficient to dissolve, to make soluble, a molecule containing about how many nonpolar carbons? So, circle 1, pause now, and circle 1. You picked this, right? 5 or 6 carbons. And those 5 or 6 carbons, why do I say nonpolar? If I'm looking at, 4 carbons, 5 carbons, those are just hydrocarbons. Again, 4 carbons, 6 carbons, those are hydrocarbons. And we said that hydrocarbons are nonpolar. So, does that make sense? What we're telling you here, or what we're discovering, is that you need to have at least one OH or one NH group, one polar group, for every 5 or 6 carbons to make something dissolve in water. If you don't have at least that many polar groups, then the molecule isn't really going to be very soluble in water. So now we've got a new way to apply that. Model 4, water solubility of selected ketones. So ketones is a functional group we haven't seen before. We saw 4 different groups: amines, alcohols, ethers, and alkanes. This is a new one. So let's apply water solubility to what we just learned to this one. So consider that water solubility. Is that consistent with the answer that you gave right here? Yes or no, and explain. Pause now. All right, so this table goes across 2 columns just to fit on the page more nicely. But we have acetone that's infinitely soluble. By the time we get to 2-hexanone, it's 1.4 grams per 100 milliliters, and to heptanone, which has 7 carbons, 0.4. So that's below our cutoff. So we say that's insoluble. The ones above this are soluble. So what do I say? Is this consistent with my earlier answer? Yes. The 6-carbon ketone is soluble, and the 7-carbon ketone is not, according to our cutoff. So one polar functional group is enough to cause up to 6 carbons to dissolve in water. All right. Some more application. Here are 5 examples of molecules below of the functional groups that we've looked at. So answer part A. Pause now. All right, so the alkanes are the only ones that are not polar. So maybe you wrote all 4. I thought it was faster to say all except the alkanes are polar. Part B. Which of the molecules can form hydrogen bonds to other identical molecules? So look at all the molecules, look at your rules for hydrogen bonding, and write the names of the functional groups down that can form hydrogen bonds to other molecules just like themselves. Pause now. Okay, do you have alcohol and amine? You shouldn't pick any others because the criteria is you have to have a hydrogen bonded to an oxygen or a nitrogen. And the only ones that show that are the alcohol and the amine. All right, but question C is slightly different. Which of the molecules can form hydrogen bonds with water? So, given that you have a molecule of water, which of these molecules can hydrogen bond with the water? So pause the video and answer your question now. All right, do you see that alkanes are the only ones that cannot form hydrogen bonds with water? If I have water, I already have the hydrogen attached to the oxygen, so that's good. The other thing I need is a molecule with a lone pair of electrons, and all of these molecules have lone pairs of electrons. So, for example, let me draw this water slightly differently so I can fit this into the space. And ether does have a lone pair of electrons on the O, and it has 2 CH3 groups in this particular ether. And so I can do a hydrogen bond here between the water and the ether because the water has the H attached to the O and the ether has the lone pair of electrons. So it is possible to have hydrogen bonding between different molecules. Ethers cannot hydrogen bond to themselves because they don't have a hydrogen attached to the oxygen, but they can hydrogen bond with something else that does have that thing. All right, so that is hydrogen bonding. If there's one theme for this class moving forward, it's about intermolecular forces. Many of the concepts that involve biochemical molecules are going to depend on understanding how these attractions between molecules work. And so it's to your advantage to really understand that here. So we've got some exercises that will assist you in that. You can check your answers, as always, on Blackboard. This concludes the screencast for Chem Activity 27. Cheers.